Okay, good morning and welcome to the Arc Science seminar. And it's a great pleasure today to have Shraddha Srivastava from Uppsala University. She's going to talk about diagram categories and reduced Kronecker coefficients. Shraddha, please.
Okay, good morning. Thank you. Good morning, everyone. I thank the organizers for giving this opportunity to speak here. And in this talk, we are going to discuss diagram categories and its connection to the reduced Kronecker coefficients, which appear in algebraic combinatorics and representation theory of symmetric groups. So the easiest example of a diagram can be given for a permutation by drawing it in certain graph. So for example, consider this permutation 1, 2, 3 written in cycle notation. Then we can draw it as a graph. We draw three dots on the bottom and 3 dots on the top and index them from 1 to 3, likewise in the bottom as well as on the top. And then we read the diagrams from bottom to top. So in this cycle, 1 goes to 2. So we join 1 in the bottom with the 2 on the top, and then 2 goes to 3. Then we join 2. Then we join 2 with 3, 2 on the bottom with the 3 on the top. And likewise, 3 goes 1. So we join 3 with 1. So this is the most easiest example of a diagram. So we see that every element of a symmetry group can be written as a diagram. So then the symmetry group algebra, which has a basis given by the elements of symmetry group, is a diagram algebra. And so we can ask what are the other groups whose elements we can draw as some diagram. So in Ashi's talk, I think 2 months ago, we looked at complex reflection group. And so let CR be the multiplicative cyclic group of order R, and zeta be a fixed primitive rth root of unity. Then the complex reflection group of type GRN is the Reith product CR with SN. So a typical element is a tuple here, where the second tuple is a permutation on n letters, and the first tuple has n tuples from the cyclic group CR. And in such an element also can be written as some diagrams. So what we can do is that, so we first write the underlying permutation diagram. So if we just for the moment forget these elements from the symmetry group, and then we just simply put these elements here. So what we can see is that an element of a complex reflection group of type GRN is actually a color permutation. We think of the element of CR as some color. And with this diagrammatic presentation, the multiplication also intuitive here. So for example, if you want to multiply 2 elements of the complex group GRN, then we write corresponding color permutation diagram. And we are going to read the diagram from bottom to top. So, so here 1 goes to 2 and then 2 goes to 1. And in this path, only zeta square is appearing. So we have 1 goes to 2, 2 goes to 1, only zeta square appears. So we have 1 goes to 1 with zeta square here. Then we have 2 goes to 3, 3 goes to 3. And then in this path, we have zeta, only zeta appears. So 2 goes to 3 and we write zeta here in that path, in the resulting thing. Now, if we look at this one, then 3 goes to 1 and then 1 goes to 2. Now 2 elements of cyclic group CR are appearing. So what we can do is that in that path, we just multiply them and write the thing. So here we had 1 zeta here and 1 zeta here. We can multiply them. So we get 3 goes to 2 and label it by zeta square.
So in principle, you could also take any group instead of CR at least, and then
we can, yes, certainly we can.
You can take G-colored permutation diagrams, basically.
Yes, absolutely. Yeah, maybe that may be better terminology. Okay, thank you.
Sorry, but how they're giving the xi to which edges? Like there are 2 edges you're putting the xi, and 1 to 2 you have not put that. What is the rule?
So you can just assume that to be identity element of CR. if I'm not putting anything here, you just that's a zeta power 0's identity.
So for example, this element represent which element of the complexity diffusion group?
This element represents 1, zeta, zeta, and 1, 2.
Oh, I see. You're just putting the okay.
Okay, so you draw your permutation and then just put the label.
From left to right kind of thing, or how you are putting?
Yeah. It's you can just say this is for h of 1. I mean, this is for the first one. For the 1, 2, 3, you can just start putting here.
Okay.
Is it okay?
Okay. Yeah.
No, not for me. Not for me.
Why?
So where, no, sorry. Maybe I'm slow. But where do you put, so in the bottom you have the zeta square is, where is zeta square in the bottom there?
This is for this one, for the top permutation. The element.
But in
this,
the bottom,
for this one we have. Okay. So maybe I should, okay, you're right. I mean, these colors can move across the crossing. So putting zeta square here is same as putting zeta square here.
So
there's some identification.
No, so zeta, so these G, as Purva was saying, G is associated with edge, not with a vertex.
Yes. So I'm, yes.
Okay, fine.
Yes. Yeah, okay. G is associated with the edge. So should be maybe edge color permutation, GH color permutation would be better.
Yeah, thank you.
So for the second diagram, you have the element zeta square, and 1, right?
We have zeta square 1, absolutely, and then whatever is the permutation.
No, I thought that would be zeta squared 1 and zeta.
That's right.
And I'm reading the color from the top. I mean, it's just made like this. Yeah.
Wait, okay, but actually I thought the edge with which it is associated are the edges starting from 1, starting from 2, and starting from 3.
Okay, but it's the ones ending, it seems.
But apparently it's the ones ending, is it? Okay.
Yeah.
Okay, that's a convention, I guess. And so
yes.
So is then the claim that the thing you have written just above, the zeta power I1 blah blah, blah tuple comma sigma, mapping to these diagrams is a isomorphism of groups then?
Yeah, it is. Yes, it is convention. Yes.
That is the correct order upstairs also, the ones where you're reading the top vertex from left to right, is it?
Yes.
Okay.
I think you have to attach it to the end because the zeta things are coming after the permutation has been applied. So
no, this matches. I mean, it is the right convention. This is slightly confusing, but
but you can construct an action of this on a set of n balls colored with G, and then this will be So because the zetas are applied after the permutation,
right.
They should
Sorry, what is the color on the edge 2, 3?
Sorry, could you please say it again?
The edge 2, 3. What is the weight on that? Is it identity?
Is the yeah. So that was the Digja. If I'm not putting anything, I'm just assuming it's an identity.
Okay.
You're not putting any
is that the first diagram above is a special case of the diagram below. So unmarked edges correspond to the trivial element.
Yeah. Right. Okay. So shall I go ahead?
Yes, thanks. Yeah.
Okay, thanks. Okay, so the symmetry group algebra. Symmetry group is related with the general linear group via the classical Schur duality. So GLNC is the group of general linear group. It acts on Cn by matrix multiplication. And since GLNC is a group, it acts on the tensor space it acts on the tensor space diagonally. And the symmetry group SK on this tensor space by permuting the tensor factors. So for example, this 1, 2, 3 act here by just permuting the places of these tensors. So this will become Vi2, tensor Vi3, tensor Vi1. So Schur looked at these two accents, and he showed these two accents commute with each other. Moreover, inside the endomorphism of the full tensor space, they generate the centralizers of each other. And there is a one-to-one correspondence between the irreducible representation of the symmetry group appearing in the tensor space with the irreducible representation of general linear group that are appearing in the tensor space. And the next one, which says there is some duality between the multiplicity and the dimension of the irreducible representations. So multiplicity of an irreducible representation of the general linear group in the tensor space becomes the dimension of the corresponding irreducible representation of the symmetry group, and vice versa. So the statement can be made appropriately, I mean, by some modification for any arbitrary field, for any infinite field at least. But we are going to work over with field of complex numbers only for this talk. And over the years, there have been many such setups for groups and algebras. So, for example, Brouwer restricted the action of the general linear group to the orthogonal group, and he showed the Schur-Weil duality between the orthogonal group and the so-called the Brouwer algebra. So when the group is small, the centralizer becomes the large. And Jones and Martin independently restricted the action of ONC to the symmetry group Sn, which sits here by the permutation n by n permutation matrices. And then they showed the Schur-Weil duality between symmetry group Sn and so-called the partition algebra. So in this talk, we are going to look at partition algebra in some detail. So before seeing the explicit definition of partition algebra, we first address some, we address its connection with some other things. So we already said the partition algebras are related to symmetry groups via Schur-Weil duality. And symmetry group play yet another role in the representation theory of partition algebra. So there, if we can realize partition algebra, so-called twisted semigroup algebras. And in the semigroup theories, maximal subgroups play an important role. And in the case of partition algebras, the role of maximal subgroup are given by symmetric groups again. And they are different than what appears in this Schur-Weil duality. That symmetric group is different than the symmetric group that they are appearing. So this was already kind of known to, I mean, Martin has been using this approach, but he did not give the term the twisted semigroup algebra. And it was formally done by Wilcox. Deligne constructed a category which depends on a complex number, which depends on a complex number, and it says that it kind of interpolates the representation category of symmetry groups, and which is now called as the Deligne's category for symmetry groups. And the construction of Deligne's category goes via the partition category, which is nice in the sense, which is also nice in the sense, by studying the representation theory of the partition category, we can study the partition algebras all at once. So I'll make a specific what do I mean by that in later slides. So specifically with the partition category, we have some triangular decomposition. And since we are looking at all partition algebras all at once, in the category, all the maximal subgroups also combine, and they give some sort of called the Cartan subalgebra. So this was a notation and also done by the Brendan and Vargas, and it's slightly different terminology was also done by Sam and Snowden. So Deligne also in his work, he observed that this partition category is a tensor category, says that the tensor structure is symmetric, rigid, and strict. And we are not going to say what is this terminology, but just to inform. And once a category has some tensor structure, its representation categories also has a tensor structure. So in particular, an appropriate Grothendieck group is going to have a ring structure. And so what Brendan and Vargas showed that the Grothendieck group is actually isomorphic as a ring to the ring of symmetric functions. And The partition category has also some connection with topology, which because this category is a symmetric tensor is a tensor category, and Jonathan Combs gave a presentation of this as a monadal presentation, and he related it to something called two-dimensional cobordism. So we are also not going to talk about this. Okay, so so one can ask if can we replace the role of symmetric group by, let's say, complex reflection group of type GRN or any group, the possible groups. Then from the viewpoint of Shraddha duality, there have been generalizations and study, and people have studied this. So it was first generalization was by Tanabe, where he looked at the centralizer algebra of GRN acting on tensor space. And then Bloss, in the Shraddha duality statement, he changed the tensor space and discovered yet something analogous to partition algebra. Then Oriana has studied the Shraddha has studied the representation theories of these generalizations. Ahmad, Martin, and Majurchuk, they looked at these from the viewpoint of semigroups. And with Ashish Mishra, I also looked at certain generalization. We basically looked at this some specific subgroup of GRN, which are index P subgroups, where P is a divisor of R, and they are also complex reflection group. From the viewpoint of categories, Liking and Savage been studying, they looked at it's a symmetric tensor category and gave a presentation and connected with several other things. In this talk, we will see a generalization from the viewpoint of maximal subgroups. So their role is quite different, though both will give the same representation theory, but the role of the symmetry group, these two roles are different. And when we want to generalize the category, we will generalize in particular the Cartan-Sub algebra to the complex reflection groups of type GRN. Okay, so now we are going to look at.
I have a question. Are
yes,
all
please.
these dualities mediated by the tensor product, or is there some other space on which both things act?
You're right. Actually, the tensor product space can be changed. So in particular, Bloss, he changed the tensor space to some other space. It's just we start with some bimodule, any algebra, and just see if they are bimodules, so definitely the action commutes. And if they generate the centralizer of each other and just check all the properties, we can work with any AB bimodule where A and B are algebras.
Okay, thank you.
So, okay, so now we are going to see a definition of a partition diagram. So they are basically a diagrammatic presentation of a set partition of a set. So a set partition of a set is a collection of non-empty disjoint subsets, such that the union is the whole set, and they can be written as a diagram. So let's see an example. So we have this set party. We have considered this set which has 6 elements, and this this collection which has a part 1, 2, 1 prime, 3 prime, and 2 singleton part is a set partition because they are disjoint with each other and their union is the whole set. And we can draw this as a diagram, as a graph. So what we are going to do is draw three dots on the bottom, index them by 1, 2, 3 prime, and 3 dots on the top, index them by 1, 2, 3. And then the condition is if two elements of the set are in the same part, then they should be connected by a path in the graph. So for example, 1, 2, 1 prime, 3 prime are in the same part. So we can join 1 with 2 and 1 with 1 prime and then 1 prime with 3 prime. And 2 prime and 3 are singleton, so we don't have to do anything for them. And the thing is that this is not a unique way of presentation. For example, we can just delete this edge and join this 2 with 3 prime. So we identify all such graphs as long as they give the same set partition, underlying set partition.
Sorry, but so do you need to have exactly a tree for each component, or can you have complete graphs on each component and so on? So how
you can have anything. You can just draw everything that you like. It's the only condition is that if two elements are in the same part, they should be connected by a path.
Achha, okay.
So it could be anything. You can just draw this also, and
Right.
that will make it do anything, all possible things. So anything. That's why I put some dots. There are more things.
Right. It is some graph between a tree and a complete graph. Okay. And the complete graph.
Okay. Yeah. Okay. Yes. Yes. And okay. So the set of partition diagram has a monad structure. Monad means we can multiply two elements such that the multiplication is associative, and it has an identity element with respect to that multiplication. It has the identity element. Sorry. Okay, so let's do an example. So we take a two partition diagram, D1 and D2, and we are going to explain D1, D2, D1 circle D2. So we have some different convention because at the end we are going to look at some left module, and if this is the best it works. I mean, so the convention is that we first write D1 on the top of D2, and we are going to read the diagram from bottom to top. So in this talk, we always read the diagram from bottom to top. And to multiply such two elements, we identify the bottom vertices of the top diagram with the top vertices of the bottom diagram. So let's do this. So by drawing these dotted arrows means we just identified the vertices. And then in the multiplication, what we have to do is just follow the paths from bottom to top. So this 1' is connected to 1, and this 1 is identified with 1', then it is connected with 1, 2. So that's a one path. So we just write here like this. And then we have 4', 5' goes to 5, and this 5 is connected to 5', and it goes to 4. So we have one path. We have one path here. And then there are things which are completely on the top or bottom, don't see each other. So they appear as it is in the multiplication. So like this we have here. Okay, so in this multiplication, there can be things which lie completely in the middle. So what we are going to do is, for the monad, we just ignore them. We don't do anything with them. And so this gives a monad structure on the set of partition diagrams. And so a partition algebra, what we are going to do, we just deform this monad, the concatenation of partition diagram that we have seen just now. So fix some scalar C, fix some scalar T in the field of complex numbers. And we are going to deform the concatenation. So in the deformation, everything is same, but except that now we are going to take care of the things which lie in the middle as well. So there are two connector components that were completely in the middle.
I guess you have to show that this actually is a composition of the partitions, right? Because there is some ambiguity that you noted, right? Going from the partition to the diagram.
Going from partition to diagram.
There are many diagrams that, unless maybe you work with a complete graph.
Yeah. I mean, I understand what. Yeah. I mean, there is some well-defined thing to be checked. You are saying this is not a graph. This is a collection of graphs. So we are choosing a representative.
I suppose you could work with a complete graph in both cases, and then. Okay.
Yeah, one could do this. Yes.
Yeah.
So in the deformation is, we'll count the number of connector components that lie in the middle. In this example, there are two of them. So we just, we multiply this diagram by the scalar T to the power 2. So this, by counting the connector component that lie completely in the middle, that gives a twisting map, which is a map from the Cartesian product of PK itself, from the Cartesian product of PK with itself to the field C. And it should satisfy some condition. And this condition is precisely says that the multiplication and the deformation of the multiplication remains associative operation. And then the this is what Wilcox basically observed, that in the partition algebra with all this definition, the partition algebra is basically twisted semigroup algebra of the monad algebra of partition monad, where the multiplication is being deformed by this given a twisting map. And in the partition algebra case, it is given by t to the power number of connected components that lie in the completely in the middle. So the monad algebra of the partition algebra, so the monad algebra of partition monad is not semi-simple. However, when we do the deformation, after a certain finitely many values of t, this partition algebra has become semi-simple. So this was proved by Martin. So specifically what is happening, I'm saying is that there exists a polynomial in one variable such that if we choose our parameter outside the zero set of this polynomial, then the partition algebra pk, here k is fixed, is semi-simple. And in fact, in the case of partition algebra, this polynomial can be given explicitly. So the deformation becomes semi-simple except for only finitely many values of the parameter.
Shraddha, in the bottom example, did you miss one path from 2 to 3?
Did I miss some path from 2 to 3? Where is it?
Because it is not matching on the middle, no? On the second
You
diagram.
disregard everything that is purely in the middle for now.
Yeah, in this part, do you miss 2 to 3?
2 to 3. Where is 2 to 3?
Just no. Just look at the bottom diagram.
This term completely lie in the middle. So that goes to that counts with the exponent.
These 2' and 3' are connected, but not the 2 and 3 and just below of it.
2' and 3' are connected here.
But when you said the diagram is 0, no, sometimes the multiplication is 0. That is when the
I did not say that. I never said here it's a monad. It's a diagram always gives a diagram. Multiplying two always give a diagram. You never get 0 unless you take your t to be 0 in the But I'm deforming the partition monad algebra.
Okay. That's okay. Great.
2 questions. So f depends on k, right? Your polynomial f.
F depends on k. Yeah, that's where I should.
And did you mean t not in 0 set?
T is not in 0 set.
Thank you.
Yeah, thank you. You're right. Sorry. Okay.
Sorry, I missed that. So what was fx?
I did not. F of x is just a polynomial in one variable. I'm not explicitly telling what it is. But in the maybe for the partition algebras, it is known what it is. So z of f of x. I just said the 0 set. We can write the polynomial from there. So we have. This is some finitely many non-negative integers 0, 1 up to 2k minus 2. So if the parameter is not in these values, then the partition algebras are semi-simple.
Oh, you're just saying, there is an f such that. That's what you're saying.
Yeah, there is extra such that. Yes.
So just one question. So what about isomorphism of these? Like if you change the parameter, are these isomorphic, non-isomorphic?
Yeah, that's a good question. So definitely, they are, when they become semi-simple, for example, choose 2 parameters. So they are isomorphic in very non-canonical setup. Because they are then when they are semi-simple, we have this Wedderburn. They are finite dimensional algebras, and if it's semi-simple, we can do the Wedderburn-Artin theorem and use. It's going to be they are going to be isomorphic, but it's a very non-canonical setup, very non-canonical way.
Okay, but these are always isomorphic as you change, even when you change the parameter, as long as these are semi-simple, right?
As long as they are semi-simple in very non-canonical setup.
But when they are not semi-simple, do we know what isomorphisms can occur among the?
I don't know. We definitely know the representation theory completely, but I don't know.
Oh, okay. So, but you know if those categories would be equivalent or?
when they are
or I mean, some
no,
of
they
them,
are
or
not
they all
symmetric.
different?
Categories will not be
They're all
equivalent.
different.
Yeah, they're different.
It's a complete answer to Pooja's question.
Thank you. Okay, so now we are going to talk about maximal subgroups. So in the theory of semigroup, the maximal subgroups play an important role. So I'll just do an example for the partition monad. So the partition monad PK has maximal subgroup. These are the symmetric groups. They are symmetric groups on 0 letters, 1 letter, and k letters, and they are very different from each other. I mean, there's no containment of each other. So for example, if we take k equals to 2, then inside the partition monad P2, then we have S0 is just 4 dots, and S1 is again just 4 thing, but we connect 1 with 1 prime, and then S2 is first, this one is the identity element, and this one is just a crossing. And we see that they are very different from each other. There's no even containment. So what is explicit definition is inside the partition monad, we have an idempotent, which is, so take a non-negative integer L less than k, less or equals to k, and just join the first L of on the first L vertices. This is just an identity strand, and on the remaining, we do nothing. So this is a idempotent in a monad. Prime to prime and prime. This lies in partition monad PL, and EL squared is EL. And then the maximal subgroup SL, symmetric group on n letters, is the group of units of the submonad, which is obtained by.
1 second. Oh, it's you have no T here.
I'm saying it's a monad. I'm taking monad. If I want to say a partition algebra, I put a T.
Monad, okay.
Yeah. So yeah, so this convention, if I want to say partition algebra, I'll say T. Otherwise, it's just a monad. Yeah.
Sorry.
So
EL, you've written EL belongs to PL. Do
you mean
SL
these are maximal among the units of the algebra? Is that maximal subgroups among the? I mean, so I'm a bit confused about the word group. So
it's a monoid, right? So
yeah. So these are actually among the subgroups. These are the maximal. Is that these are maximal? I mean,
maximal. I mean, that explicit definition is basically if you take a idempotent and consider the monad submonad is lie inside here, is multiply right. EL on left and right. This is a submonad where identity element is EL now, and we are looking at the full group of units inside that monad. That's the maximal subgroup index with L.
Yeah. Okay.
Just one.
But oh, sorry. Go ahead.
Yeah, these ELs are primitive. Like, is there a reason? So these are maximal, right? So is there a special reason for these ELs, or these are all the idempotents?
These are all the idempotent up to some notion of conjugate. So it's not in the representation theory terms maximal. It is maximal in terms of monad, and what we study the theory of monads, finite monads. So we basically take any idempotent, and you look at if you have M monad and look at this submonad EME, and you just look at the group of units. That's idempotent. That will give a maximal subgroup SE. And the thing is that two idempotents, for example, instead of working, if I still have the L of the strands, but I move one strand to some other vertex, those are conjugate in the monad by an invertible element. So we identify them.
Okay, thanks.
I'm still a bit confused. So are these actually among the submonoids of M, which are subgroups? Are these maximal?
I mean, The maximal is precisely, yeah, these are all, I mean, I did not understand your question.
No, there's a sort of notion of maximal, which just means that there is nothing that contains it in that class, right? So is there a class of subgroups among which these are maximal in that sense? So if you look at all the subgroups of this monoid M, that's a class of groups, right?
So yeah, so the thing, if you look at the a group of, I mean, no, it is not maximal in that sense, sorry. So the thing is that if you look at the partition monad PK, then the subgroup is SK, the full subgroup. This is the largest one.
Yeah.
Right. And it is here.
And those but you said these are not contained in each other. So
exactly, they are not, because they are coming from so the definition of maximal subgroups it's coming from here, from the submonad. Take an idempotent, look at the submonad, multiply E both on the left and right, and look at the group of units there. So for example, if you take EL, sorry.
Yeah, so just to get more concrete, so if I take S in particular, SK does not contain S0.
It does not.
Here. Okay,
Here.
so SK is just a symmetric group in the usual sense. Is that right?
Yes, yeah, okay. Yeah.
So what is S0 then?
S0 is also a group of unit. It's just the unit is here is not the unit of the monad, it's the idempotent E.
So what is the order of S0?
1.
But how can it not? Oh, okay, I see. Okay, thank you. Yeah. So it's a group, but its identity is not contained in S.
Yes, yeah, their identities are quite different.
Yeah. Thanks for clarifying that. Yeah.
Okay, so from the representation theory of these maximal subgroup, we can actually construct these simple modules. So in the theory of monads, what is important is Green's equivalence classes of left-right relations. We are not going to say in the detail, but the relevant one is the Green's left class associated with the idempotent EL, which collects all the partition diagram D such that you multiply D on the right of the partition monad PK, and that as a set is same as multiplying EL on the right of the partition monad PK. So and if you look at the linearization of this set, then the symmetry group SL acts on the right, and the partition monad or even the partition algebra is going to act on the left. So we can take any module here and tensor it with this to get a module here, the left module here, and that is what Paul Martin did. He basically so we know the representation theory of symmetry group or the field of complex numbers. Then we know the simple modules are indexed by the partitions of given by integer partitions, and suppose lambda is a partition of L, and S lambda denotes the corresponding spec module of the symmetry group SL. Then, as we said, this CLE is a bimodule. Is a PK. We can actually put a T here as well, and SL bimodule. And so if we tensor any representation of SL on the left, on the right, then the resulting thing will give a module of partition algebra. So this module is called a standard module, and a simple module is going to be a quotient of this module. I mean, if the algebra is semi-simple, in that case, this will be a simple module. Otherwise, if it's not semi-simple, then it's a quotient of a module.
I just had a question. So I just wanted to know what kind of elements occur in the left class. Is it a subset?
Yeah, it's easy to see. So you need to, for that, you need to recall your EL. So your EL is identity up to L and then something. So on the left class, So okay, so you just basically need so on the bottom also we have from L plus 1 all the way K it will be all singleton because they were all singleton here, and here you just no, I'm sorry. Okay, I need to go back. Sorry. So these ones will be singleton. They don't adjoint anything. And then here you just have a L propagating blocks. So here you have exactly L of them, and they are just connected any fashion you like. And you should have L of them here.
Okay.
So yeah. So symmetric group SL is going basically act here by permuting these things, and the partition monad acting on the top as we multiply the diagram. So what Paul Martin did is like he constructed a bilinear form on these standard modules, and in the simple modules is basically that W lambda modulo the radical of the bilinear form. And when the parameter t is 0, then we need to exclude L equals to 0 case. We need to exclude because in that set of bilinear form turns out to be identically 0. And but if the parameter t is not 0, then everything appears. In particular, the simple modules of partition algebra are indexed by partitions of all non-negative integers up to k. Okay, so now we are going to relate the representation theory of partition monad with the reduced Kronecker coefficient.
Could you
Yes.
go back one slide, please? In the case t is non-zero, W lambda itself is not irreducible.
I mean, W lambda could be
Reducible.
Could be reducible, but it could not. I mean, it depends. The bilinear form.
I see. So L
I'm not
lambda
saying,
is a quotient of W lambda. Okay. And in the 0 case,
in the 0 case, the partition that this something like this will appear when L equals to 0.
so lambda cannot be empty, or so. That's
Yeah. Yes. That's the precise. The lambda cannot be empty. And in this case, lambda equals to empty is also allowed.
Okay. Thanks.
Because we can invert T and still, so the bilinear form is non-zero. Okay.
Thanks.
So we are going to relate the representation theory with the reduced Kronecker coefficient. So first, we need to recall what is this. So we start with.
Is the picture that for all non-zero values of t, you have the same number of irreducible representations, but for non-generic values of t, there are extensions between these? Is that because?
Yeah, you're right. Yes. In the when the algebra is non-semi-simple, there can be extension between the.
So, but the dimensions don't change. Dimensions of the irreducible.
Dimension of W lambda does not change. L lambda will change.
Okay.
So we start with any partition lambda. Let's say it has R parts, and we take some positive integer n, and we pad lambda with n to get a partition of n, as long as we have a. So okay, maybe say it better. So lambda padded with n has R plus 1 part, where the first part is given by n minus mod lambda, and the remaining parts are given as a part of lambda. And this is a valid partition as long as n minus mod lambda is at least lambda 1. Then if you look at the diagonal action of the symmetric group Sn on the tensor product of the spec module S lambda n and S mu n, since we are working over the field of complex numbers, everything is semi-simple. It breaks into simple modules again, possibly with multiplicity. And Shumurnahan showed that So these multiplicities which depend on n says that if you take n to be infinity, take n to be large, take n to be infinity, then this number turns out to be this limit is finite, and he called it to be reduced Kronecker coefficient. So in general, a computation of such a coefficient is a difficult problem, and Amri probably can tell us even what is this complexity. So let's do an example. So for example, if we look at the, if we take the tensor product of these two spec module, which is here, it's just easy, just sign with sign, and we know it is a trivial representation. Okay, so now if we increase the first part of the partition, and then take the tensor product again, and then we see there are more components appearing. And if we further increase, we see one more component has appeared. And if we do once more, then the number of connected irreducible, they kind of now stabilize. And also, if we just kind of forget this, just forget this. So these are the up to, if we mod out by n, the first row of the partition, then they look exactly the same. So in general, if we take n to be at least 3, the decomposition turns out to be this, and their multiplicity is also stabilized, becomes stable. So now we want to relate these reduced Kronecker coefficient to the partition algebra. So before going to the partition algebra, so we recall something which is already is a well-known. So we have a sure-while duality. On the right-hand side, symmetry group is acting. On the left-hand side, GLNC is acting. So let's start. Let's assume that K is also varying. Then we can consider the Young subgroup SK cross SL inside the symmetry group SKL plus 1. So SK plus L. And we induce a irreducible representation to the full symmetry group SKL and look at its multiplicity. And it is known that it is same as taking the Kronecker tensor product here, or just the diagonal action of the simple module here, and look at the corresponding multiplicity of simple module. And it is known to be Littlewood-Richardson coefficient. We know how to, there are algorithms to compute that. And we have a sure-while duality between partition algebra and symmetry group Sn. So Bowman, Derbyshire, and Oriana, what they showed that the Young subalgebra of partition algebra, we consider its irreducible representation, induce it to the bigger partition algebra, and look at the multiplicity of the irreducible, and that turns out to be reduced Kronecker coefficient. So we need some condition on the N and K, because the things may not be semi-simple here. So we kind of see that already more than 2 partition algebras are appearing in the same picture. So it would be kind of nice to have one specific category where this tensor product is happening, and we are looking the multiplicity of some space in that. So so the partition algebras.
So wait a second. N is for this n is bigger than or equal to 2 times K plus L will assure that these partition algebras are semi-simple. That's what you're saying.
Semi-simple. Yeah.
Yeah.
Yeah, actually, maybe I should have said, sorry. If I want all of them to be, I should have written n bigger than or equals to 2K and n bigger than or equals to 2L. This will imply this one, because I want these to be also semi-simple.
Okay.
Thank you.
But you may want K plus L also to be semi-simple?
Yeah, that will be implied, because then if n is bigger than or equals to 2K and sorry, what I'm talking, maybe everything we need. Let's assume everything. Yeah, assume all the partition algebras are semi-simple.
So that's why you put this n bigger than or equal to 2K plus L.
Yeah.
Okay, thank you.
And that bar is the limiting value, or it's the value at n?
Is the limiting value, is the reduced Kronecker. Oh,
Okay.
sorry. There should be no n.
No
here.
ends.
You're right.
Yeah.
No ends here. It should be just the reduced Kronecker.
What's your best estimate for the stabilizing n?
Okay. Sridhar knows this answer. I
I
think.
keep getting
He has written his
confused too.
thesis.
I also get
Well, this is
confused.
something like that. I think it's something
Mod
mod
of
lambda,
plus
mod mu,
plus
mod
mu.
mu. Okay, Sridhar is telling something
It's-
by 2. I mean, I checked it. I think Oriana has given this kind of.
Oh, it's given in Oriana. Okay. Yeah, I keep getting confused about this point.
I thought it was sum of the two partitions plus the first part of the third partition, like mod lambda plus mod mu plus mu1.
Oh, plus lambda 1 only.
I
And
thought,
no mu.
but I'll check and wait.
So there should be a sharpest case, I guess. So many places they just give some bound, right?
Yeah, it is just bound. I'm not saying this is the sharp bound. This is bound.
So anyway, we can discuss this at some other time.
Okay. So I'm really running out of time.
Here you're saying for any value of n bigger than that, this answer is the same, and that's the Murnahan value.
Yes.
Okay.
Okay, so partition algebras, if you fix a parameter t and vary your k, then they fit into a tower of algebras. So specifically, you take a diagram D, and if you want to embed it in the next one, take T and put just a vertical next, right to the right of it. So there have been studies of it's the representation theory of tower of algebras. There we require all the algebras to be semi-simple. So for example, one can do a Konko-Varshik approach. But as we know, in the case of partition algebra, when we vary k, fixing a t, vary k, after finitely many step, everything is going to be non-semi-simple. So perhaps there should be some other approach to study that. And one can do this using the method of using the language of partition category. So that's our next target. So a partition category has objects given by non-negative integers.
No, I didn't understand that last comment, Shraddha. Could you repeat that, please? When you are fixing t and varying k, therefore?
Yeah. So I'm fixing a t and varying k. Then after finitely, because the condition should be, okay, so let's say t equals to be precise, t equals to n, some fixed non-negative integer. Then the semi-simple condition is n should be
take a value which is not an integer, and then I'll be all right.
Yeah, then you will be all right. If you take t to be which is non, then everything is semi-simple. You can try to do a Konko-Varshik approach then. Yes.
Okay.
But if t equals to n and if you vary k, this condition is going to be violated.
Okay.
Yeah.
Yeah, I think don't worry too much about time. Those who attend this seminar regularly know that we often go over time. So,
okay.
Yeah.
Thank you. Okay, so we define partition category, which appeared in the work of Dillon, and so it says objects given by non-negative integers, and the morphisms are morphism from the object L to K. It consists of the partition KL partition diagrams, because we are reading this switch is because we are reading the diagram from bottom to top. Oops. So I should say so here you see that earlier in the partition diagram, when we defined, we looked at L equals to K case, but in principle, one L could be any, there is no guarantee, there is no, it is not necessary that the top and bottom should have the same number of vertices. If you think even from the set partition viewpoint, or everything that we said before. So what we can do is, so I have to tell how do we compose two partition diagrams. So if we cannot compose, then in that case we define it to be 0. This situation will happen if here the number of vertices are different than number of vertices here. So then anyway, we don't compose two such morphisms. So And if we can compose, then the multiplication is same as in the case of partition diagrams. So what we put D1 on the top of D2, identify vertices in the middle, and follow the path, and things which lie in the middle, they give the exponent of T. So let's complete the example. So we identified things in the middle and follow the path, and we end up getting a diagram. And there are 3 things which lie completely in the middle. And so we get T to the power Q. So this is the composition of two diagram morphisms in the partition category. Okay, so to study the representation of partition category, one could pass
sorry,
to...
Shraddha. I'm sorry. What do you mean by basis? Basis?
Now I'm defining a C-linear category. So the homomorphism space should have a
so these are vector
space
spaces.
structure.
Okay.
Yeah. So these are vector spaces where the bases are given by these type of diagrams, partition diagrams.
Okay, thank you.
So in particular, maybe I should say that if you look at the endomorphism algebra of an object here, then that's precisely the partition algebra, not equal to the partition. So the partition algebras in the tower now have become the endomorphism algebras, but there can be more morphisms between when the things are the top vertices and bottom vertices are not same. This is PKT. This is our partition algebra. So in this category, the endomorphism becomes endomorphism algebras are precisely the partition algebras, fixing the T. So to study the representations of partition category, one can actually pass to some locally finite dimensional algebra, and one can do it directly as well, but that would require more terminology than this. So a path algebra of a category is just basically the direct sum of the homomorphism spaces. So this is definitely not a finite dimensional. It is going to be, but it is something called locally finite dimensional. And so we define the meaning of locally finite dimensional, but before that, we need a definition. So let us denote one n by the identity partition diagram on n vertices. So it is given by basically, so we have n dots on the top, n dots on the bottom, and it is just n strands. That's all. Then sorry, I should have copied. 1 minute. See. It's not working, it seems, not pasting. Okay, great. I'll just draw it in that case. Just n strands. And then the path algebra has this idempotent decomposition, where this is just rewriting the thing. There's not much happening here. This home space is basically, we can definitely multiply things on the top and bottom, the corresponding identity elements, without changing the algebra. And these each of them is a finite dimensional, because we have only finitely many partition diagrams. When you fix the number of vertices on the top and bottom. So this is a locally finite dimensional.
Do you need some condition that 1n par
yes.
1n is equal to par is a union of those things or something? That every
just
element
need this
of
idempotence to be orthogonal. That's all.
No. So an algebra of this kind is locally finite dimensional if there exist
Orthogonal.
if there
There is
exist
this
orthogonal
idempotence.
idempotent such that you also need that every element can be in the subalgebra generated by the idempotent. Yeah. Okay.
Yeah, it's a direct sum. Will that be okay?
Yeah.
So there exists some indexes.
And those are finite dimensional. Okay, got it.
And
Thanks.
yeah, these are finite dimensional and these are idempotents. And they are orthogonal.
You're right. Thanks.
What I'm doing in that. Okay. Then we see that every group algebra of symmetric group is inside the path algebra. This is for all k now. So basically the maximal subgroups which were inside the partition monad, when we are considering all the partition algebras, they all are going to appear in the path algebra now. And another observation is which is kind of relevant, because we said that if we study a partition algebra, then we can, if we study partition category, representation of the partition category, then we can actually recover the representation of partition algebra. So this is the point, because the partition algebra turns out to be an idempotented centralizer algebra of the path algebra. So pk of t is precisely then this is multiplying by idempotent 1k on left and right. And then we know some general theory how to recover the, if you know the representation theory of bigger algebra, then we know the representation theory of idempotent centralizer algebra. So now, but one can see this part is pretty much infinite dimensional. So how do I study its representation theory? So, but it has some nice, interesting decomposition, which is which looks similar to the triangular decomposition of a universal and appealing algebra of a finite dimensional complex semi-simple algebra. So let's address that. So before, but we define it, we need to do an example that will motivate the decomposition, that will motivate the triangular decomposition of the full algebra. Okay, so yeah, so let's take some examples, say some partition diagram on which has the one is connected to 3, then 3 is connected to 2 prime and 3 prime, and then 2 is connected to 4 and it comes down connected to 1 prime, 5 and 6 are singleton, and 7 connected to 8 prime and 8 is connected to 7 prime, then 4 prime is just here, and then 5 prime is connected to 6 prime. So what we are going to do is that look at the top part of it. Look at first the top part of it and arrange the top part in certain manner. So we have 1, 3, and then we have a 2, 4 on the top, and then we have 7 and 8. We forget the things which are completely on the top. They are, if the things which are not coming down, let's forget for the time being. And then we can arrange them in a order. So because arrange them in the terms of their maximum entry. So 1, 3 is smaller than 2, 4 because we have a 1 here, 2 here, 7, 8 are not. And then 2, 4 is less than 7, then 8. So what we are going to do is,
in this example, maximum entry and minimum entry have to give the same order. But you underline the minimum entry. So is it maximum?
Am I entering the minimum entry? You are absolutely right. Okay. 1 minute. What do I mean by maximum entry? I mean by the minimum entry. Sorry.
Okay, that's
minimum
the usual
entry.
way of writing set
Yeah.
partitions.
I want minimum. Yeah, I want minimum. Absolutely. Thank you. So we have this 1, 3. You first write 1, 3, and then connect 1, 3 with 1 prime. Then we have a 2, 4, and connect 2, 4 with 2 prime. And then we have 5, 6, which are not coming down. We don't do anything to them. They are as it is. Then this 7 is coming down to 8 prime to something, does not matter to what it comes down at present. So we just connect 7 with 3 prime. We are kind of doing in this order. And then this 8, we look at 8, this 8 is also coming down. So this 8 is connected to 4 prime. So we had order, maybe I'll just quickly write that. 1, 3, less than 2, 4, and less than 7, this is less than 8. So we connected 1, 3 with 1 prime, 2, 4 with 2 prime, 5, and sorry, then 7 with 3 prime, and 8 with 4 prime. We did it in an order. And now do the same thing for the bottom, which it can be done. Not going, if somebody has question, I can say, answer that. But now in this decomposition, we have totally disregarded what happens when the things are crossing or something. So we have to compensate that by putting some element of symmetry group here on 4 letters, symbols. So in this example, we need to do this crossing here and here. So in particular, this decomposition is unique up to just that here one could just put anything, any identity element here. 1, 4 here and 1, 4. Apart from that, this is unique. And in this example, as we see for this decomposition, we really need to work with the partition diagrams, which may not have the same number of vertices on the top and bottom. So it's the best. So we should look at all partition diagrams. So what we got is that we could write D as a D minus. I call this to be D minus, and then sigma, and then D plus. So why D minus? D minus is actually there's some kind of grading here going on. So D minus is because it has a less number of vertices on the bottom than the number of vertices on the top. And anything for the permutation, it's always something like grade 0 because number of vertices on the top and bottom will always be same. And for the things in the bottom, we have a same number of, we have more vertices on the bottom than the top. So that's why this symbol comes the plus. This is some convention. Then consider this submodule inside the path algebra, which are spanned by such D minus diagram and D plus. So par plus is all the diagrams of this form, and they should be in this order. And the number of vertices on the top is less equal to number of vertices on the bottom. Okay. So Sam and Snowden, and they did in some different language, but Brandon and Vargas, that is, we are exactly discussing their work here now. So if you look at this locally unital ring, so this is not a unit, I mean, it's a locally unital ring. And on this ring K, everything is a bimodule. I mean, this par char, par plus, and par t, everything is a KK bimodule. And what they showed is that this party is actually admits this kind of a triangular decomposition where we have, now they are giving the analogy because this one can think of from the Lie algebra, think of this element here as some kind of negative root, an element here from the cartan, an element thing from the positive root. So that is their terminology. And in fact,
except the cartan is not abelian.
It's not, but it's semi-simple.
Ah, okay.
So that's the point. It's not abelian. Of course, it is very far from abelian, but it's semi-simple. So we can still do some representation theory, looking from the cartan. So, and in fact, Brandon and Stroppel, they have a big paper on the idempotent, on the algebra admitting a triangular decomposition and how to construct a representation. They have several terminology. The important thing is to have a algebra to have some kind of idempotent decomposition, and we always work with some fixed choice of orthogonal idempotent. And there are, and it's not just that, and there are more data that require, I'm not saying this here. So what they call is the thing here to be the direct sum of all symmetric group algebra is the cartan subalgebra of the path algebra of partition category. And this is semi-simple. So as in the case of semi-simple Lie algebras, we can start a representation here and then make it a representation of so-called the positive border and then induce it to the whole algebra. So what they did is, so here, so we define some, this is analogous to the positive Borel. So look at the Cartan subalgebra and tensor it with the, whatever it's called, the negative root, sorry, positive roots. And then you take, so simple modules of, now the Cartan subalgebra, they are given by all non-negative integers. So if you take a partition lambda, and then S lambda is the corresponding spec module, we can make it as a module over the par sharp by letting this par plus act as 0. And then we induce it to the whole path algebra. And this is what they call it, the standard module. And then, as we said, as the simple modules will be, the simple modules of the path algebra are now one-to-one correspondence with the simple modules of the Cartan subalgebra. And okay, so I should have said, sorry, I don't know, it was there, but anyway, I should say then the this is a Verma module, and then how this is a standard module, and the simple modules are this module is still, this standard module has a unique maximal submodule, and so the simple module is given by taking a quotient of the standard module. So one can construct a simple module as well from the Verma, as exactly in the case of highest weight representation for finite dimensional semi-simple algebra. Okay, so now we are going to discuss the ring structure of the Grothendieck ring of some appropriate Grothendieck group. So before that, we first observe that the partition category is a tensor category. This was appeared in the work of Deligne. So for the objects, the tensor product is just simply given. So for the objects, objects are here integers, and the tensor product is given by their sum. And the tensor product for the morphism is also quite intuitive. We just put the D1 tensor D1 here, D2 here, and then just reindex the vertices of D2 to get a to get a diagram morphism. And then since party on the tensor product on this partition category gives the tensor product on the tensor product for the modules of over the path algebra. We are always looking the left modules. So in particular, we have some bi-module, which is just it's a party comma party tensor party bi-module. So this is just ordinary tensor, and this tensor means here. And so if we take two bi-modules, if we take two left modules over the path algebra of partition category, then their ordinary tensor is a left module over the party tensor party. And then if we tensor this module, if we tensor this module with this bi-module, then it becomes a left module over. Then this becomes a, this is basically party mod, locally finite dimension. And the next result of Sam Snowden and also Brandon and Vangas, which is not at all an easy statement, proof require a couple of pages, is that if we take two modules, locally finite dimensional modules, which has a filtration by the standard modules, then their tensor product also has a filtration by the standard modules. So in particular, if you look at the Grothendieck group of the category of locally finite dimensional modules, which has a finite delta filtration, then the Grothendieck group has a structure of a ring. And Brandon Vargas, so inside the Grothendieck group, we have now, inside this Grothendieck group, we have a, and the base is given by the images of the standard modules. And they prove that the, with respect to this basis of images of the standard modules, the structure constants are given by the reduced Kronecker coefficient. And in fact, this Grothendieck ring is isomorphic to the ring of symmetric functions. Okay, so this was the story about partition category or partition algebras. And Yeah, so now we are going to see some colored version. So in the beginning, we said we start with a permutation diagram. We can color its edges by an element of symmetric, by an element of cyclic group CR, and we get a color permutation diagram. So if you want to do the color partition diagram, what we should do, we look at the connected components of the partition diagram and color it by the by elements of the cyclic group CR. So for example, take any partition diagram and just put some number, just put any element of CR in connected components. And so naively, this is what should be a color partition diagram, but one should also, if you want to multiply, then we see that somewhat a multi-parameter will also appear. It's better to work with multi-parameters. Okay, so let us define it. So we are going to define a multi-parameter color partition category. So suppose we have some R tuples of complex numbers. Then this category has object given by non-negative integers, and the morphisms from object L to object K. There will be linear combination of KL color partition diagrams, and so I need to explain. So this color thing is kind of understood that we are looking color partition diagram. So the term color is okay, but why multi-parameter? So when we try to multiply two color partition diagram, we do exactly exactly as in the case of partition diagrams and as in the case of color permutation diagram. So what we do, we follow the path, and if in a path there are more than and all the colors appearing in a path, they get multiplied. So for example, here this get combined, and this gives this path here in the resulting diagram. So here we have a zeta, then we had a zeta square, then we have a zeta. So we get zeta power 4 here. And likewise, we can do for everything. But now if you look at the connected component that lie completely in the middle, they can have potentially different colors. So in the middle, for example, this lie completely in the middle. This has color zeta cube, but this has a color zeta square, and this has also color zeta cube. So we should look at the multi-parameter version of it if we are doing a really generalization. So in this example, there are no color of identity. There are no connected component with color identity. So we have x0 power 1, and then we have x1 power x0 power 0, x1 power 0, because there is nothing of color with zeta, but we have one connected component with color zeta square. So we have x to the power 1, and then we have two connected component completely in the middle with color zeta cube. So we take it precisely just what I've written here. So we multiply by this monomial. Okay, so we can look at the path algebra.
Sorry, Shraddha, could you? Yes. Here, see, you conveniently wrote a very simple diagram. What if I have complicated? I have a doubt about basic definition. So, so there could be several things could be connected, right, in the partition algebra.
Yes, absolutely, yeah.
So, for example, 6, 7, 1, 2. Suppose we connect. I mean, where do you draw? I mean, the edges that yeah, 6, 7, and 7 could be connected to 5 as well, right? Or
yes.
Okay, you're only considering. I mean, let's connect 6 to 2 as well.
Yeah, connect 6 to 2.
Yeah, and 6 to 7.
And 6 to 7.
Right. Now, where do you put the colors? Where do you put the color?
Okay, good question. So it does not matter as such, because we can put anywhere that we like, and what matters in a path, colors are allowed to move anywhere they can. So if we had, if here the total color for this path, we can write like this, and it can also zeta to the power 5. we multiply. If they are more than one color on a path, we just multiply them.
Okay, so instead of a path, I just think of an equivalence class of a set, right? I mean, there is some equivalence class, and that to that equivalence class, you associate an element of G. Is that?
Yeah.
I mean, to that subset.
Yeah, we can define color set partition. Yes.
I see. Okay, thanks.
Okay, so we looked at the path algebra of the multi-parameter color partition category, and like in the case of partition category, this also has a triangular decomposition. So which is a giant work with Mazurchuk, and so where now the role of the complex, the role of Cartan subalgebra, where in the case of partition category it was played by symmetric group algebras. Now it is here played by the complex reflection group. And this definition of C power minus, C power plus, they are slightly different than in the case of because of the colors on the top and bottom can be completely in the top or bottom. So this is slightly different, but not very different. So and we know the reducible representation of complex reflection group are indexed by multi-partitions of length R. So this is just, I'm saying that it has R, these are all partition of R tuples. And we can define like a positive model, and also we have the standard modules, everything. And then as in the case of partition algebra, the multi-parameter color partition category also has a tensor structure. And we proved that the tensor product of modules having a finite delta filtration has a delta filtration. And here in this proof, we require more things to do as in the case of partition category. So there were several settle points in the sense, because our modules so the modules of complex reflection groups GRK, they are not self-dual, and there was a lot of things that we need to adjust. We need to pass to some other setup. So, but this is the result that I'm just saying. I'm not saying it's an obvious statement. And in particular, then the growth indie group has a growth indie group of the category of finite, and the growth indie group of locally finite dimensional modules over the path algebra having a delta filtration has a structure of a ring. And then we computed the structure constant with respect to that basis in the grothendieck ring, and we showed that these are given by the product of reduced Kronecker coefficient, R-fold product of reduced Kronecker coefficient. And then we also to prove that the multi-parameter color partition algebra, the algebras are generically semi-simple. And we had also some proof that the additive Karobi envelope of the multi-parameter color partition category is a generically semi-simple. So this result for when we take R equals to 1, this is Deline's interpolation category. And something I will end this with this result. We also proved that the multi-parameter color partition algebra is cellular with respect to the involution, where we flip the diagram, but we don't invert the color. That means it's not G goes to G inverse. We invert, but we don't invert the color, because when you invert the color, things are not, the simple modules will not be self-dual. So there's this kind of subtlety over there. And this result about the cellularity of this actually kind of follows from the general methods. We did not have to do too much. But since for the partition algebra, there have been now several proofs, I thought to say this result. Okay, thank you for listening.
Well, let's all give Shraddha, thank Shraddha for this lovely talk. And now let's see if there are questions. Just please unmute yourself and ask.
Yeah, the obvious question is why not take a general group, maybe a finite group? Why only cyclic group?
Yes, we could take, there are satellites in the sense, so we need some kind of order on the set of simples. We need some kind of upper finite, like, I mean, if you're looking for the G, it's just the Reith product, probably you can work with that. But if you want to replace this by any finite group, or they are anyway working.
No, I meant G. G is any finite group and G Reith SN.
Okay, yeah, that is possible. That is possible. We can, sorry. Yeah.
But
So
then
some of
what
the
is the
results,
partition algebra? I mean,
we can define this.
No, it's colored, no? G colored.
G colored. G.
No, the SN is not the coloring. No, it's the G. Yeah. So she's taking G to be cyclic group.
Yeah, but that's just multiplication in the group. That you just multiply all the colors.
Yeah. No, so I thought you were saying replace SN by some. Oh, take G to be SN. I see. Okay.
There will be some satellite. I mean, I think up to here there is no issue.
Non-abelian.
When we try to prove this kind of, sorry, yeah, even that. But when we come up to here, I'm not sure about this, because we had to really work with explicitly with the representation being self-dual or not. And for the case of CR Reith SN, taking G goes to G inverse is not a self-dual thing, but we can do something else. We can do like we invert the diagram, but don't invert the color. So this non-self duality is appearing because of this CR. If R is bigger than 2, is not, the representations are not self-dual. So I'm not sure about this one. There will be some issues here. This one will work. Up to here, this will not be, because this is all diagrams and all, we can decompose it. But I'm not sure about this. That when we want to explicitly prove it, the tensor product has, I mean, some kind of, I mean, give some ring structure on the within the group. I'm not sure if
I suppose you can also replace the SN by some by some bigger group, like the CN type or TN type or something.
Yeah, you mean like some index P subgroup of GRN or something like that?
No, I mean, there's a theory of partition algebras for type BN and DN, right?
Those are different, very different from what we are doing here. Those are coming from Schur-Weil duality, and they sit, and some of them actually sit inside the, so there are two things actually, there are two generalizations. So one generalization, they simply sit inside the partition algebra, bigger partition algebra itself. And another one, because we change the tensor space, the diagrams are different, but that's not a monad, I mean, at all. The things can multiply and give a zero thing. So I think what Assis has talked, it is, these things are different in nature, because we really focused on the thing should be a monad and it should be a generalization.
Yeah. Any more questions?
Yeah, I have more questions. But so I am just trying to understand this. What was that?
Path algebra.
Yeah. Party. Let's say T is generic. Its irreducible representations are every partition is the set of all partitions, right?
Yes.
Is for every partition there is a irreducible module.
Simple module. Yes.
Simple module.
Yes.
Yeah.
Yes.
Okay. And and when I tensor them, I do get the multiplicities are given by the Moore-Lohan stable values. Is that the lesson? Is that the model, or is there some?
If in the case of generic semi-simplicity, in the case of generic semi-simplicity. Otherwise, in the non-semi-simple case, we do not know how to multiply simples, but we know how to multiply the standard modules.
Yeah. No, let
So
me
here-
just take the case simple. Let's do the generic case.
Mhm.
So if I take two simples corresponding to two different partitions and tensor them, the decomposition is given by the multiplicities are given by the stable the Moore-Nahan values that you talked about. Is that
Yes.
correct?
Yes. Yes, that is correct.
I see. Okay, thank you.
I just have a follow-up question to what Raghavan just asked.
Yes.
Yeah. Sorry. So this reduced Kronecker coefficients that you will get when you decompose this product of simples in the generic case. So there are some conditions on lambda mu nu under which the reduced Kronecker coefficients just become the usual LR coefficients, right?
Yes.
Don't they become
And they are the
C
same
lambda?
size. Yeah.
If
Then
mod
they are
lambda,
all the same size. Yes. You're right. Yeah.
right? If mod lambda plus
Yeah.
mod mu is mod nu or something like that.
Yes.
So then
Sure.
does that mean that in that sense, see, then there it sort of gives you the correct numbers that you get in the classical Schur-Weil duality, right? Meaning C lambda mu nu is sort of what you would get if you work with GLN representations. So I'm just wondering, is there, if you make that special assumption on lambda mu nu, is there some way of actually transporting these modules to that classical Schur-Weil duality setting and saying that, is there a sort of a way like that of showing that these reduced Kronecker coefficients coincide with the LR coefficients?
I need to write. So let's just here in generic semi-simple setup, and it's assume that mod mu is same as mod lambda plus mod mu, and then you are saying this is what we just said, and then says, is there a way if it can be transport this to be then this becomes this to show this. We come by some procedure here to the, let's say, symmetric group. I think yes, we can. This is because of our Cartan subalgebra. They're kind of restricting. Okay, that won't be semi. Yeah, I don't know, but okay, let me write it. So this is if we commit to not S lambda, tensor S mu, tensor S nu. And this I'm doing for, you can do this for Cartan subalgebras. Is this the question? It can be how somehow come here from, and then it will show that these two things are equal.
Are you doing it for more like GLNK, right? Meaning, or
more like GLN.
For SK, it is more that induced product.
Yes, that would be inducing. Yes, because
something like that. That's what I'm asking. Yes.
Yeah. So for the tensor product, so this tensor product is pretty much like when we are doing kind of SK cross SL plus L. Because in the tensor product, what we do is that we will get precisely this kind of embedding in this tensor product for the symmetric group. When you look at inside the Cartan subalgebra, we are basically the tensor product. What we do, we have some K diagrams. Some K diagrams here, some L diagrams here, and the tensor product is basically putting things next to it. So the things on K and L, they don't interact, and that is precisely the embedding of the Young subgroup of SK cross SL inside SK plus L. So, but the question is, how do I come to the modules? Maybe, I think it's possible. I want to say that I can have this because of this condition on the partitions, I can write this?
I think it's easier to go the other way. Like if you have GLN modules, then
how should I go to GL? I mean, yes, I would like to go if we have
the
some
all
pseudo-value
ones
validity.
weight space.
Wait, okay.
And then that's a representation of Sn. We saw this when we were working with character polynomials, right? There's some homogeneous top degree part which behaves exactly like symmetric group representations, and then there are sort of lower degree components when you take a representation of Sn and GLN and restrict it to Sn. And that top degree part is just coming from the all ones weight spaces. And there the tensor product of GLN representations behaves just like this induction, sure induction.
Yeah, the only thing is that here, I mean, for the partition algebra modules, I do not know what is the meaning of taking weighted space 1, 1, 1.
No, I was saying for GLN.
For GLN, yes, for GLN it is fine. Yes, but I'm trying to see
here it should be taking the restricting to the Cartan subalgebra, I suppose. Yeah,
that is what I'm also thinking. But I'm not sure if I'm actually I'm able to think what he's asking. So this should my suspicion is that this doublet will reduce to the, because of the condition and the definition of the tensor product, and the condition on the partition, this will reduce actually the computation here, because in the generic semi-simple case also the simple modules, what it is, they are actually induced from I mean the positive Borel kind of does not see there, and we have S lambda here. That is what we do. These L lambdas are like this. Yeah, okay. And these functors are these are functors which are monadal. So I can the monadal from the Cartan. I think the answer to your question is yes. But let me. I'm not sure if I'm able to say it correctly. So the L lambdas are like this. And our end partial to party, this as the functor from, okay, I need to do this little bit more. This should be monadal. What should be, but I should write it one more step clearly. Okay, let's do this. Write it. So this inflation means I'm just the thing which have a positive grading, they act as 0 and S lambda. And then this int partial party with this functor, this should be monadal. I mean, this should preserve the tensor structure. And so, okay, so this is a functor from where to where? This is a functor from the Cartan subalgebra to this side. To this side, to the whole party modules. And then here, then on the Cartan subalgebra, the tensor product is precisely the external tensor product. So I mean the Cartan subalgebra, we take two modules here, and so that the tensor product here is the precisely induction, this kind of thing. Okay. It looks answer looks to yes to me, but I'm not sure if I'm able to say it.
Okay, yeah, thanks. Sort of a similar question in the same line. Your colored partition algebra wala coefficients are, again, you say they are products of reduced Kronecker coefficients, right? So yes. Again, is there some sort of at the module level, there is some reason why this should turn out to be products of things which appear in the usual partition algebra setting?
Okay,
I
so
mean, it's a
answer
sort of
for
a similar question.
yeah. So for the at the level of ring of symmetric function, it is clear, but not actually modules, because we don't have a sure while duality statement. So what I can actually, this I learned, I think, one of your talk only. So we talked about lambda rings for the symmetric functions, and here I have some space. So here the Grothendieck ring turns out to be a tensor product of. So this is my ring of symmetric function, and you just take R-fold tensor product here. So I can write more here. And so here in this case, the Grothendieck group turns out to be isomorphic to this. And the ring of symmetric function has some non-homogeneous bases. So those deform Schur function such that their ordinary tensor product, just as you multiply polynomials, is the reduced Kronecker. Is the reduced Kronecker. And then for our side, what is happening is that this, if you look at the isomorphism of ring of at the level of, I mean, this has isomorphism as a ring, then these fellows are going to I'm going to write the lambda ring notation, which I learned from I think one of the workshop from you only. I think it's written as something like that. It's a bit complicated. It's just the lambda ring of something will appear, a lot of things. Okay, so I can write more explicitly. It will become something complicated, something like that. Xij should be some big sum, something like that. I is from 1 to R. And then since here, so this is just a normal tensor product. So if we just denote that this big expression of symmetric function to be just as tilde lambda, the multi-partition, then their tensor product in the lambda ring, we know this here, we multiply two things here in this notation, then this ordinary multiplication just goes the component wise. So this one is, if you want to understand this, which is same as these coefficients. This is expected at the level of symmetric functions. I'm not sure about modules.
Okay, thanks.
If I figure out all the details in that previous question, I'll send you an email.
Okay, so any more questions? Okay, I guess if there are no more questions, let's thank Shraddha once again.